Please join me in welcoming Keynote Jeff Houston. Jeff is no stranger to the NanoNod community, having been on stage over 20 times. Who here has seen Jeff before? Oh, good. So he's kind of self-introducing. Jeff is most noticeable for his pivotal role in bringing the internet to Australia in the 1990s. His current role at APNIC enables him to focus his research on addresses distribution policy, internet infrastructure, IP, and more. He's also a great v6 guy. Jeff, we look forward to your outlook and comments on whatever happened in IPv6. Please bring Jeff live.
G'day, my name's Jeff Houston, I'm with APNIC. Let me first apologise for actually not being in Toronto. I can only blame myself, well actually I can blame my bicycle. I was having a very pleasant bike ride last weekend and managed to hit an obstruction and the bike stopped. Me? No, straight over the top. And you know, if you look at young humans, they tend to bounce. But the older you get, the more bouncing becomes bumping and grinding and sliding, which is what I indulged in, and managed to ruin parts of my body, including fractured ribs. So look, I'm out of action in terms of flying here. I did mention to my doctor, look, I'd like to fly up to America next week, and he said, so here I am. My apologies for that. If there's one thing I've learned from that, and I was wearing a helmet, but let me say to everyone else on a bicycle, if you don't wear a helmet, you're a lunatic. I'm only here because of my helmet, and I'm sure there are many others with a similar story. Always wear a helmet. However, that's not the reason why I'm here. The reason why I'm here is to actually talk about IPv6. And I kind of wonder how many v6 presentations you've sat through. 10, 20, 50, 100? I'm like, this saga has been going on for years. And I'd actually like to offer a different take on IPv6 in the next few minutes. We'll spend a little time on this, because you know the program folk have given me a fair deal of time, but I will come up early because I'd like to leave some time for comments and reactions, because I'm not sure the message that I've got here is one that's commonly shared. May just be me, who knows? But look, let's explore this issue. And let me start with some work I have been doing for more than 10 years, which is measuring the adoption rates of IPv6. This is the daily chart of all over the world using a sampling technique based around the presentation of online ads, using a sampling technique across the entire internet. How many folk can, if you will, get an object if the only way to get there is v6? And that's the blue line here, you know, what I call v6 capable. If it's all v6, then you know, can you get it? The red line is a subtle variance of that. It's called v6 preference. If it's dual stack, which one would you prefer? Now, in general, if your ISP has got the routing right, if all other things are equal, if the DNS is equally quick, etc., happy eyeballs means that most applications will prefer to use v6. So in most of the cases, the red line and the blue line should be the same. But interestingly, for many, many years, there've been at some variance that despite v6 being around, for some users and in some parts of the world, it's just slow enough that it's a preference to use v4. Not a serious issue in most cases, but nevertheless, it's sort of noted here as being persistent. And I suppose the question about this 10-year-old graph of every day for 10 years is, this is a pretty standard internet curve. I'm like, it's slow. It's not, you know, in a year, it's a decade. But it is up and to the right. Yes, like many other curves, we're just on a journey and it's just going to happen, right? Until you add that vertical scale, because we really haven't done very much at all. the amount of V6 out there is just under 40%. And it's taken us 10 years to get to even there. And if you consider the starting gun for V6 was fired way back, not in 2014, not even in 2004, but back in the 90s, then this is almost geological in speed. This is taking an extremely long time to get not very far at all. So the whole reason for V6, as I'm sure most of you will remember, and those of you too young have been told this, we did V6 not because it was a Wednesday and we had nothing else to do. We did V6 because it was indeed an issue around V4 exhaustion. And the RIRs have handed out their last V4 address over a decade ago. We've been in a state of exhaustion and running the internet on empty for over a decade. And yet the uptake of V6 is just a little over a third. Now, dial the clock back 10 years and say, is this likely? No one. No one in a nanog room, no one in any room on the planet would go, oh, yes, highly likely. It's completely unexpected. You know, we're in this kind of no man's land of having no V4 around and not doing V6. And it's kind of, what's below us there? What's keeping the network working? Magic, I guess. It's completely unexpected. And if we use maths, because we can, and take the trend line from 2018 to the present of V6 adoption, least squares analysis for those of you mathematically inclined. I haven't done anything simple. It's a linear trend. So it's just saying, look, that looks a lot like a straight line. Let's just project it forward. Then you end up with another 2 decades. 2 decades. This is insane. I'm like, it's silly enough to go, we're a decade or more after exhaustion, you know, what's going on, everyone? But to say that this weird hiatus is going to take another 20 years, I'm like, you're joking, right? What's wrong with us as an industry? Us as a sort of the folk driving the global communications enterprise, that we can't even achieve this simply and quickly and directly. 20 more years of trying to hobble along with this sort of V4 exhaustion state is just insane. So what I want to ask is not, oh yes, let's do bright, shiny things with V6. No. Let's look at the darker side. What's gone wrong? How did we stuff this up? Why? Which I always think is a fun kind of question. So let's head into the time machine. Whoop. And let's go back about 35 years. And we're going to land in August 1990 at the IETF, which I think, Vancouver, could be wrong, somewhere on the West Coast there. And Frank Zielinski came up with a really interesting presentation. Now, you'll notice a few things about August 1990. This is a pre-PowerPoint year. You know, we used to actually sit there with these acetates and write out our slides by hand, as Frank has done. And then the rooms were equipped with overhead projectors. Most of the time, the bulbs worked. And so when you see these kind of slides, yes, all the slides were like that. We just used to write this out by hand. The technology of making it bright and shiny and good, like you're seeing in front of you on the screen, came a little later. But anyway, Frank's slides. At the time, we had divided the IPv4 space into 3 classes, A's, B's, and C's. A's had 8 bits of network identifier, 24 bits of host identity fields. And so there are only really 256 A's in total, if possible. But of course, we only used half the address space, so 127 A's. They were big enough that we stopped handing them out. And even by 1990, they were difficult to get. You needed to be enormous. Apple, DEC, HP, not many others. The early universities did get one, like MIT, but that was a long time before that. And then there were Class Cs. Class Cs had 24 bits of network identity space and 8 bits of host. So you could build your networks with up to 256 computers. Now, around the 1990s, the personal computer revolution was underway. You know, the IBM PC had made its mark. Everyone was building personal computers. And all of a sudden, the day of the mainframe was over. So building a network with just 256 personal computers loaded into it was kind of, why bother? So it was pretty clear. It was a bit like Goldilocks, you know, Class A's too big, Class C's too little. Class B's with 16 bits of identity and 16 bits of host, 65,000 hosts, kind of matched what we wanted. And so B's were being shot out the door of the internet like they were going out of style. And indeed, what Frank showed was that by March 94, just 4 years on from his presentation, there'd be no more B's. Oops. We were going to actually run out of Class B's, which was a disaster. Because at this point in 1990, we were just getting over the OSI stuff. We were developing a pretty bullish attitude that the internet really was an incredibly viable solution. And it was spreading all over the world. And then Frank came along and said, nah, ain't going to work. We're going to hit the wall. And so we panicked, obviously. And a few quick hacks appeared. The first one, which was very effective as a short-term hack, was just get rid of classes. Just get rid of classes. No more class A, B, C. Everyone actually carried around, this address has so many bits of network identifier and all the rest is for host. So you could tailor your own network to suit your sort of number of hosts you were trying to connect, which actually removed a lot of the inefficiency in the address space. But we recognized, particularly as the personal computer was very quickly going to become smaller and faster, and although the idea of having it on your wrist was indeed an incredible dream, there were some dreamers out there in the IETF even then. And if you think about how many of these things they're going to make, well, it's in the scale of billions. So in some ways, this was only ever going to be a short-term hack. The longer-term solution was build a better internet, which we did. And up came, after some years of debate, argument, etc., the glory that is IPv6. Don't you love that photo? I think it was Russian. It is amazing. You also wonder if it ever actually worked. And I swear, this is not AI. Genuine photo. Bizarre. IPv6, after a bit of a beauty contest through 92, 93, IPv6 came out as being minimal. There were many far more radical ideas, but IPv6 was based around a thing that was called SIP, Simple IP, and it really was, at least in the first instance, recompiling the IP code with the constant 32 replaced by the constant 128. And so you expand the address fields fourfold at 128 bits, and that was it. There are a couple more things happened here. At the time, packet fragmentation had been getting a pretty ugly name. Some work by Jeff Mogul, much the same time, sort of pointed out that packet fragmentation was making anything that was dreamt of going high speed or efficient not. It was just evil. And so that was removed from on the fly. If you really wanted to fragment the packet, send a message back to the source, the original sender of the packet, going, too big, slice and dice finer. Routers were no longer allowed to apply fragmentation on the fly. Probably a mistake. And the second thing is we replaced ARP with multicast. Many reasons why, but I think the major reason was that one of the principal architects of V6, Steve Deering, had just done his PhD in multicast. He had to be given something. So the venerable address resolution protocol with broadcast got replaced by a whole bunch of multicast, which, as it turns out, has been a mixed blessing. But the issue is that IP was never a relay network. It was never push it forward by one hop, reassemble everything, push it forward another. It wasn't a forwarding protocol. It was an end-to-end protocol. And so if someone is speaking 32-bit IP and sends the packet out, then a 128-bit IP speaker can't do anything with it. And similarly, when they send out a 128-bit IP address, the 32-bit speaker goes, I'm sorry. So we could never, despite our best sort of English words going, let's make it backward compatible, because that's the way transitions are going to work. The issue was it wasn't. It was always going to need to be almost a two-horse race here. We had to run some kind of dual stack transition process of running both networks at once. Now, interestingly, we'd done the same only a few years before. If you dial the time machine back even further, mid-1980s, and look at what was on most campus networks and some of the sort of emerging corporate networks, you'd find across those Ethernets and various other broadband LAN solutions, you would find IP, you would find DECnet, you would find Novell NetWare, you'd possibly find some SNA, you'd find all kinds of protocols sort of there together across the same network. And we're running many stacks at once. So the concept of V4 and V6 was not entirely alien. Now, there were some folk who said, well, hang on, I can take a V4 packet and given enough intelligence in the middle, I can spit out a V6 packet. I can do network level proxies or translators. The answer is, yeah, you can, but incredibly insecure and very, very easy to turn hostile. And the answer was, well, let's just not do this. Let's just run a very simple dual stack transition. It'll only take a few years. Sorry, did I say that? Yes, it'll only take a few years. Let's just move on. And so what it meant was that everything, hosts, networks, everything, was going to be equipped with two protocol stacks. As I said, that wasn't exactly foreign. The age of multi-protocol networks, was still around. And so adding another protocol to the mix wasn't exactly alien, but that's the way we went. Now, the last flag day in IP was way back, early 80s. The network by the late 80s, 90s, was just too big to just do it. So we needed this transition plan. We needed to sort of gently push into a dual stack world slowly without necessarily getting everyone to do something on the same day at the same time. Now, we had some assumptions here, and I think they're pretty good assumptions. Start early. Why? Because it's going to be doubly hard if you don't have enough V4 addresses to keep you running. If you've run out of V4 and you go, oh my God, we need to do V6, you're too late. And that's a message for today as much as it is a message for, the early 90s. And secondly, we had just kicked the telephone companies out. No one was in charge. No one was orchestrating anything. This transition was going to be driven by local individual decisions to deploy dual stack. There's no forcing function. The internet's driven as a market. And the last of this assumption, which as it turns out was entirely wrong, was that this entire transition would be fueled and driven by long-term common sense. And it would complete before we ran out of V4 addresses. So the first ideas were on paper, looked okay. Some early pioneers, some early adopters sort of did dual stack networks, probably at the edges. They probably weren't connected. This wasn't going to build from the middle out. It was just going to be little bits and pieces of innovation all over the place, and we would connect them via tunneling. So some initial dual stack deployment would have islands of V6 connected by running IPv6 within an IPv4 tunnel. Anyone remember 6 to 4? Anyone remember Teredo? There was a fair few of these kinds of solutions. And in fact, part of the problem, I think, was that we didn't just invent one or two. The IETF at one stage, there's a slide up somewhere, 35. It's kind of, dudes, overachieving. Stand back, stand away from the keyboard, and stop it. You're just confusing everyone. So the second part of this, because tunnels are bad. Tunnels are incredibly bad. This whole thing about packet fragmentation, tunnels only make life infinitely harder and infinitely worse. As anyone who's tried to do these kinds of overlays would readily acknowledge, it just doesn't scale. And so 6 to 4, 20% drop rate. You can't build a service with a 20% failure rate. Teredo, oh my God, 35% drop rate. Great technology, apart from the fact it didn't bloody work. Oops. So the next part of this transition, however, was get rid of the tunnels, which is actually a really good idea, and retrofit these transit networks with V6 so that the edge networks, when they deploy dual stack, can actually speak V6 end to end. And by and large, this is today. Oddly enough, it didn't take a few years. It took, 30. Oops. But it's largely where we are. All the networks that, are out there are sort of retrofitted with dual stack V6 support. Yeah, and that's kind of the way it works. Now, the final outcome, which is yet to happen, is that there's no point in running V4 anymore. And as a bunch of local decisions, it just gets shut down. I'm like, who runs DECnet anymore? I'm sure there are a couple, but on the whole, it's gone. How? Local decisions. Just no point anymore. So this final outcome, folk who are running V4 go, well, why bother? I haven't got customers using it. There's no point. I'll just shut it down. There might still be some residual islands, but somewhere through application level gateways and a bit of creative natting and protocol translation, do what you need to send it across V6. And the network then gets back to this single protocol purity. Cool. Great plan. Problem solved. Yay. All hosts preferred to use V6 when there was V6. The transition had just happened because as network operators enabled V6, hosts would go, yes, I can do that. And so there was nothing more to do. And so by about 95, we kind of said, well, that box is ticked. I don't need to do anything. I just need to wait. And so we turned our attention elsewhere and just waited. Now, something happened. And I would actually blame somewhere around here. I think I have a very, very early iPhone. This is a more recent one. It's by comparison quite big, actually. They were tiny, the first ones. Very impressive. But mobile telephony became mobile data, became mobile smartphones. And this whole idea of numbering every attached device became insane because the number of address allocations we were doing around the 2004 to 2008 started to ramp up like crazy. We were allocating hundreds of millions of V4 addresses every year. In 2009, 189 million addresses got sent out from the RIRs. And in 2010, it lifted to 248 million. Now, the whole network only had 4 billion addresses that were usable. And so this was a problem. We were eating up all of that space because the mobile phone revolution in particular just simply ripped out all of that assured future. We never saw it coming. We never, ever saw it coming. And so by 2011, we're in a bad place because you see, the plan that we had, this gradual takeoff, that sure, the internet was going to grow across this period. And yes, we will continue to use more and more V4 addresses. But as long as the rate of V6 deployment was sort of accelerating faster than the level of the growth of the internet itself, and we were retrofitting older networks with dual stack, then as long as we had this momentum, and as long as we completed this before we used the last V4 address, we never needed to use the last V4 address. By the time everyone had done V6, happy eyeballs, preferring V6 meant, what's the problem? Everyone's doing V6. Let's just walk away from V4. So it's a great plan. I'm like, it's a fantastic plan. I like it. I think I even believed it at the time. But by about 2010, things were going pretty badly. And as I said, it was the pressure from mobile devices. This is a busy slide, but the green line is the count of addresses that had left the regional internet registry factory. And it's measuring it by /8s, and there are 234 usable /8s. And so by 2011, that great pool in the sky of unallocated v4 addresses, IANA, ran out, February 2011. They gave away their last blocks of /8s to the RIRs, and the RIRs factories were just pounding out v4 addresses every day, 300 million a year. The routing table was also seeing phenomenal levels of growth, the blue line. The count of advertised addresses over that period was getting up to just under 150 million addresses. The red line is the unallocated address pool. And again, this is a bit bizarre, but oddly enough, that pool was growing. Now, even though addresses were under, I think, quite extraordinary pressure, there are a number of folk going, no. I'll just keep this address, tucked into my armpit here. It's okay. I'm ready for a rainy day. Okay. And so IANA ran out of v4 addresses in February 2011, and only a few months later, the first RIR, APNIC, ran out of its free pool of addresses and was left in this weird sort of last /8, where if you applied and you're appropriately humble, faced east, on your knees, all that kind of stuff, you'd be lucky and you might get a few Class Cs. Yeah, it kind of, in some ways, rationing's worse than nothing. And the RIRs did have long debates about how to manage exhaustion. The community consensus was keep some in reserve for the most compelling cases, for the late entrants, give them something, not nothing. And so we're down there in the bottom right of this graph, giving out tiny amounts of addresses for some years after 2011. But, the real answer, of course, and if you consulted the v6 working groups, was v6 is the answer. Problem was, by 2011, anyone who was looking at v6 found that the number of users as a percentage of the user population who could use v6 wasn't even 1%, a third of a 1%. This is a graph from Google, an early graph of folk visiting Google. And interestingly, you see this weekday spike that enterprises were sitting there going, no, not even slightly. And it was really the sort of consumer ISPs that actually had more of a momentum here of doing v6. And again, this is red versus blue, total versus native. Tunneling was pretty popular even up until 2011, despite the fact that it was crap. It's amazing, folk who were advertising tunneling, how much they hated their users. This stuff just didn't work. And it also says a lot about the persistence of users to sort of press through even in the most adverse conditions. And 6 to 4 in Teredo was certainly as adverse as it gets. But the true message here, we'd run out, but there was no v6 coming up. It was just not adhering to the plan. And the plan had just been smashed into tiny pieces because we're in a non-space. By the time we'd run out of v4, v6 was meant to be there. We weren't meant to run out of v4. We were meant to have completed this. Whereas in actual fact, we were nowhere near it. So the revised plan looked pretty ghastly. Here's the plan in 2011. And somehow we had to lift v6 deployment from below 1% to 100% of the internet and do this within a 7-month projection of how much longer we've got. Unrealistic. Never, ever, ever going to happen. Because if you think about it, the size of the internet at the time, just under 2 billion users, about 1 billion net hosts, lots and lots of routers, firewalls, stuff, billions of lines of code, all that stuff. We had to do everything in 200 days. There wasn't the money, the organizational capability. or even, the will to look at this. It was much better to simply put your head down and go, no, no, not happening, not happening. State of denial. Did someone mention climate change? No, no one did. So the plan in 2012, if you could call it a plan, wasn't a plan. It was sort of, we are here. There is no V6. The internet is still inexorably growing. We've run out of V4. Oops. And that's where we found ourselves. Now, it wasn't completely bereft. There were a number of folk in the IETF who looked at network address translators and said, that is an invention of some satanic demon. It completely destroys end-to-end, it adds fragility, it makes everything more difficult. Do not go there. The industry said, I've got no choice, dude. I've got no more, if you will, pristine addresses to give out one to every mobile phone, one to every customer's device. I'm just not doing this. As we're done with the dial-up internet of some years before, and then the emerging DSL internet, you hand customers dynamically one address to say, while you're connected, here's an address, use it wisely and share it among your hosts in your home, and, share and share alike and translate like crazy. The answer was NATs. And despite the IETF refusing to standardize NAT behavior, particularly for UDP, which was, as it turned out, I think a major error on the part of the IETF that let attitude get in the way of pragmatic standards, NATs just took over the entire internet. This is how we actually managed to make it work. It's very low friction, very, very low friction. You can deploy NATs in your network. The decision of whether I deploy it in my network or not is an independent decision. Servers can deploy it or not in various ways. Certainly clients, up to them. Servers don't need to be involved in this. Clients initiate a service transaction, and for the lifetime of that transaction, you get an external address and a port binding for the duration. And particularly with TCP, when the fin packets fly, everything gets handed back. Here, use this address somewhere else. Servers, oddly enough, are in central data centers, and they can use name-based distinguishers to share the underlying IP address. So you can have a whole bunch of different whatever, and they all can translate to the same IP address, the same platform. But when you actually create a connection, you say, I'm going to www.jeff. And the answer is yes, well, I'll put you in the Jeff context against the common server using the same IP address as everyone else who actually accesses that server platform. So NATs are pretty amazing. And what it's done is allowed the internet to work for over a decade, close now to 15 years, way beyond the fact that when we ran out of networks. So we've been actually fueling most of the network's growth on V4, and the dual stack transition, bizarrely, is still underway, but there's no longer any great exhaustion pressure. We went over that, we're beyond that, and so the impetus is now different. There are some other changes, though, and there's an Aaron meeting later this week in Toronto. And for a little while there, 2008 through 2010, RIR address policy meetings were pretty hot things, because the folk who were doing the rationing of the available V4 addresses, the manner of rationing, who gets it and who doesn't, were oddly enough pretty hot topics. But these days, no. The process of distribution of IP addresses is now markets and market pricing. We're reverted back to classical Marxian economics and using markets as distributors of these sort of common goods. And oddly enough, because of issues around centrality, it's actually the large content distribution networks that are totally dominating this space. NATs around at the edges for clients seem to be picking up the job adequately, that it's kind of working. Your internet and my internet seems to work, even though neither of us are using real, unique IP addresses. But it does bring up some questions, and I think they're good questions. How much longer? Is it really another 20 years? How big is the internet when we go that far? What will the silicon industry do to us? When we start to price addresses, is this really fair in a world of great disparities of wealth? What about fairness of access? Who gets cut out? Who gets advantaged? What is the total cost here? Who benefits? And what are we achieving? But I think there's something else here around the law of unintended consequences. Because is this really heading on the path of, well, ultimately we'll just get rid of all this stuff, get rid of markets and everything else. We'll go back to a pure, pristine world of the 1980s with V6 substituting for V4. Yes? It's not happening, is it? We're wedged on transition. And I'd actually bring up some sub-cases of that larger up and to the right. And one of them is where you are right now, and where I should be too. North America. By mid-2019, the transition to V6 across that entire continent stopped. The major service providers had done their job, and everyone else thought, don't have to do anything. There's no urgency. I'm meeting my requirements functionally. Meh. So it's around 52% and has been now for some years and showing no sign of moving. Oddly enough, particularly in North America, there is no impetus to continue the transition to V6. It's just a status quo. Interestingly, through the years of COVID, the amount of V6 actually declined a bit, picked up slightly in 2022, and then it's kind of stabilized. So maybe it truly is 20 odd years to get to the end of this. Maybe this really is the trajectory we're stuck with. Although trying to figure out how we can do this is insane. This is completely wrong. Now, I would actually argue that the reason is it was easier for the internet to change its entire architecture than it was to do this transition to V6. The architecture of networking in the 1980s, a very strict addressing-based architecture. Names were just aliases for addresses. Addresses were everything. We don't operate in that mode. My mobile phone, and neither yours, doesn't have a unique IP address to communicate with servers. We just borrow an ephemeral token and use it for the duration of the transaction just to stop the network getting streams confused with each other. The real issue is I communicate with services by name, not by address. The address is merely a convenience. And all of a sudden, when you don't need public addresses uniquely assigned globally to number every host and every service, if you don't need that, then at what point do you actually think there is address scarcity? Because I would actually argue that over the last 20 odd years, the salient feature wasn't the transition from V4 to V6. That was noise. Follow the money. You see, in the classical internet, it was the network itself that was the gateway, the rationer, the arbitrator of a scarce resource, communications. Because to get to a service, you needed to use this scarce resource called networking. And it was the network service provider that actually had to do the work in giving you access to some service that was remote. And if you're running an ISP in the early 1990s, the dominant costs were actually the cost of moving traffic. And whether you actually did your own network and built your own wires and so on, or whether you paid the onerous costs of transit network operators, no matter which way you did it, that was the cost base. Networking dominated all cost. North America, less obvious than, say, Australia. The network I was running in the late 1990s, 70% of the costs paid by consumers were to actually ship the traffic in and out of the country, was actually moving data. And so that was the dominant cost. And the role of the transit providers, absolutely dominant. And if you go to a NANOG meeting of that time, or you look back at what we're talking about, there were two things. Routing, and peering in transit. And they were the dominant topics of conversation because that was where the money was. The ISPs were the brokers of this scarce resource of distance capacity. Apps and transport, incidental in terms of cost. That's not the network we live in now. And there are a number of factors that have changed what was scarce into a totally abundant resource. For many years, the entire moving data around the planet, there was much more demand than there was capacity, and price was used to actually arbitrate who gets to use it. But these days, when folk are building terabit cable systems, they're not doing it to give me faster access to Europe or Singapore or anywhere else. They're used by CDNs to actually push just in case copies of data and content that I might access and to get there before I actually needed it. Capacity in the global system now completely outpaces demand. If you look at it, what's actually happened has been a continuing outgrowth of Moore's law. Because certainly in the world of fiber, the better the digital signal processing and digital modulators, the more capacity you can put into the same piece of physical fiber. And this look at the last 10 odd years in fiber has gone from 40 nanometer chips with 8 terabits of capacity on a single fiber system. And this was in 2022 with 5 nanometer chips looking at around 64 terabits per second. I think that number in 2022 is actually low. We're doing around 2.2 terabits per lambda and 190 gigabaud signal rate. So the fiber capacity is actually slightly over that, around 100 terabits per second. The chief distinguishing there, if you look at it, is the processing capability of the digital signal processors from 40 to 16 to 7 to 5. Current state of the art, Apple's M3 chip, I think, is 3 nanometers. So in some ways, capacity is actually an outcome not of better fiber, it's of better silicon, more capable silicon, able to do better signal detection in sort of cable environments to squeeze more capacity into that fiber cable. So the silicon revolution has completely changed communications. But as well as that, of course, it's the compute power itself. By 2020, we're up to 50 billion transistors per chip. We're pushing. We're going to go up to 1 trillion gates per wafer, per chip very, very soon. It's just has an inexorable momentum that is almost awesome in its mechanical delivery of compute power. Computing is not scarce. Computing is totally abundant. And this doubling every 2 years seems to be persisting. We've seen the end of Moore's law being predicted continuously. And I too find it hard to believe, where do you go after 3 nanometer chip technology? Because, there's only about 10 or 15 silicon atoms in around 3 nanometers of silicon. At some point, the electrons will just go, stuff it, dude. I'm just going from collector to gate. I don't care. 3 nanometers is tiny. 1 just seems unbelievable. But, somehow the physicists out there keep on delivering. And thank God they do. So, yes, abundant compute power anyway. And the last part of this is totally abundant storage. Here's the unit price per meg of storage. This is a phenomenal slide. It actually goes back to 1955. And just the cost of storage. It's never been so cheap, and it continues to drive down. So what we're finding is, of course, as we move across, from core to spitting rust, to small drives, to flash, to SSDs, etc., the cost of storage is continually going down. So what did we do with all this abundance? The rationing stopped. And instead of doing on demand, you want to have this resource, you want to see this content, let me take you to wherever it happens to be on the planet and deliver it back. We went, no. Let's deliver a copy of this content to the front door of every ISP in the world. The front door. Yeah, but isn't that weirdly difficult? The answer is, well, if you think about it, there's just 6,000 transit ISPs. If I can deliver a piece of content to 6,000 points, and that's not that many, I'm adjacent to every last mile access network on the planet. And so all of a sudden, just in case, coupled with abundant communications, abundant storage, and abundant processing, just in case makes sense. All of a sudden, the entire internet has eliminated distance. I pre-deliver everything you might need as close to you as I possibly can. And the network now is no longer your packets go around the world. Your packets go across your access network and hit the local data center, and that's it. Packet miles have shrunk to just a few kilometers for many, many, many people. Shorter networks are bigger because all of a sudden you're only driving across short distances. So all those tricks around transmission capacity are so much easier when the lengths are short. So we can get lots and lots of platforms delivering service in aggregate across many different regions. So all of a sudden, coupled with high capacity mobile edge networks, this is a network that has no trouble pushing petabytes out to users. We've stopped pushing them across the network itself and said, look, don't care. I'll pre-deliver, I'll pre-provision, and now we're going to serve from the edge to the user. The distance is tiny. We can scale that up far faster and far more effective than any other way of doing it. Distance is also makes things difficult. All the protocols work astonishingly badly once the delay between the two ends gets high. If you can squeeze that distance down, all of a sudden you can make incredibly efficient protocols. You can actually make the network deliver quickly. And coupled with sort of 4G and 5G out there in the radio access networks, we're now looking at gigabit style networks almost everywhere. Compressed interactions, shorter distances, high capacity circuitry. The internet's fast, really fast. And at the same time, because we're pushing a whole bunch of service and silicon to every edge, we're now doing a better job. We're now able to make encryption for everything, not just viable, but a reality. Because at this point, it's not an expensive luxury. It's just a commodity that all those edge servers are able to accommodate. We're encrypting and sealing up networks to make them less leaky, to make them less prone to external attempts at disruption. And we're even pushing further with oblivious DNS and oblivious HTTP to isolate knowledge of the querier and the content from any form of onlooking. We're actually now able to build a network where applications and services treat all network infrastructure as uniformly untrustable and create a secure layer above that that works at speed and cheaply. It's amazing. And again, at this point, abundance simply brings you economies of scale. We're actually doing a huge amount of this by capitalizing on advertising, for better or worse, that's what's happening. But the interesting social result is that a former luxury service that was only available to a few at high price is now a really affordable mass market commodity. It's an everything issue. It's what public communications was always meant to be. Everybody, all the time. It's cheap. So in all of this, the money moved. The network is not the critical resource. It's not the bottleneck. Applications are now where the money is. The internet billionaires don't build fiber and wire anymore, well, with the exception of Elon, who's building satellites, but that's a different story. The money is in applications and services. All the money is now up at the eyeballs of the network. And so V6 kind of gets lost. I'm going to do V6. Is someone going to pay me more for my network service if I have dual stack? And the answer is, dude, don't care. The user base and the content world don't really care if you do V6 or not, and they're not going to pay. So IP addresses are not the critical resource because NATs have managed to sort of plug this sufficiently well that this is not an address-constrained network anymore. And any investment in a V6 transition is largely an investment that you're doing because it's a Thursday. You're not doing it because more customers, lower cost, greater resource utilization efficiency, because it won't. It just won't. And so the currency of networks is no longer addresses being the critical service point. It's different now. It's now the currency of networks is altering, because today's network is a network of names. It's largely a service that uses CDNs in all kinds of forms and fashions, and it pushes replicants of content and service as close to the user as they feasibly can get. And so TLS and the underlying issue of service name indication is now the critical sort of selector feature that actually gives you the multiplicity and scaling factor that allows the network to grow another billionfold. And although you might say the DNS is horrendously cranky, groany, doesn't work very well and insecure, true that it's what runs the internet. Do we do routing? No, not really. Because if you're adjacent to every access network, what are you routing? There's no intermediary transit networks. If your average AS path length is, say, 1.1, you're not routing anymore, you're switching. And that's important. Most large content networks, the content of the internet, is sitting inside routing tables with an average AS path length of 1. It's the DNS that's performing routing, not the routing protocol. It's the DNS that's doing the closest match to, where are you? Where's the closest point of access for that service that I can steer you to? Hi, DNS, here's an answer. So most of today's internet traffic is switched and not routed. So it's names that are driving the internet. The authenticity model of names that we're using in today's network is actually TLS. DNSSEC, too little, too late. In fact, it started before TLS, but it still didn't do enough of the job. DNSSEC is largely a market failure. And if you're not routing, does anyone really care about RPKI? Because in a routing-free network, routing security doesn't matter. It's a routing-free network. The name-based framework that underpins the entire internet security framework are the certificates behind TLS. I'm not saying they're good. I'm not saying they're robust. I'm saying it's what is. This is the network we run on. These days, DNS outages are globally catastrophic. Look at Facebook's 24 outage a couple of years back when they, managed to lock themselves out of their own buildings. Slack with its problems some time ago as well. DNS outages can be terrible. CDN outages are also phenomenally catastrophic. Routing outages, they're just annoying. And these days, badness is actually all about DNS abuse. It's not about address abuse, and it's not about routing abuse. It's actually about name abuse, because names are the new internet architecture. Because as we moved from end-to-end peer-to-peer into client-server, we replaced this whole idea of single platform servers and unique addressing into replicated servers without a network, because that's what CDNs are. And clients, they aren't identified with unique IP addresses. They're transactional entities. They just borrow an address to complete a transaction, and the next transaction they just borrow another. And if you look at applications like Quick, you can even switch the IP address of the client mid-session, and Quick kind of goes, oh yeah, fine, I can cope. Individual services don't need their own IP address, thank God. It's all DNS based. That's the architecture we're moving in. We've moved completely from address-based networking into name-based services. And there's a whole bunch of implications around there that V6 has been caught up with. So this slow uptake of V6 is not because we're chronically stupid or short-sighted, or at least if we are, V6 is not the outcome of that. There's something else going on here, because we've been able to take a 1980s based architecture and scale it a billionfold by changing the core reliance from the distinguishing tokens of addresses eked out in this old fashioned with bookkeeper ledger keepers, thank you RIRs, into a name-based system that actually has a huge amount of hierarchical delegation. And we're able to span the job outward through delegation structures that allow us to scale far more efficiently and far faster than we could ever have done with addresses. And names effectively are far more extensible. And so if you think about it, having a problem with the finiteness of the IPv4 1980s address-based architecture, the solution wasn't to just have another 1980s address-based architecture, which is what v6 really is. There are a few stupid, annoying differences, but it was longer addresses that was the only redeeming feature in v6. It was no point because it didn't really solve the larger issues of scaling. We needed to move, and we did. So in today's network, names really matter. The DNS really matters, which if you look at the way in which we actually administer names today on today's internet, you should be worried. Whoops. Names really do matter. Addresses, not so much. They're temporal tokens to use to distinguish things. Someone said time was really nature's way of making sure everything didn't happen all at once. Addresses are almost a similar thing. They're used to separate the flows on a network to make sure they don't get confused, but they don't actually identify endpoints anymore. And therefore, address-based routing, not really important anymore. We switch, not route, as I've talked about. It's a different kind of world because as we push everything out of the network and over into the application infrastructure, even the transmission infrastructure is abundant. We don't have to bring consumers to service delivery points. We bring the services to consumers. The application is the service, not just a window to some remote functions being done on a server somewhere else on the planet. The longer term trend is to actually eliminate the network from networking. And you kind of wonder, do networks matter? What defines the internet? Well, they're all doing the same address plan. Well, no. I actually think it's a disparate collection of services that just simply share a common referential mechanism and a common namespace. How you move the packets around, well, up to you, dude. Doesn't matter. Is there something after v6? And I would actually answer no. There's nothing. It's a 1980s concept whose time has come and gone. And now, it's not that we're going to all of a sudden stop it because it's markets, no one's in charge. We'll keep on running this for a while, as long as it's not expensive to run. But I don't think it's got any future. Endpoint addressing is just not there anymore. It's all localized, and it's all automated to the extent where it's localized that addresses are relative, and that's good enough. Naming and namespaces, yeah, it's a hot topic. Is it the DNS? Are we stuck with it? Are there other name forms? Should names be more consistent? Blockchain names and so on. There's a fair deal of work going in there. As to the value of that work, that's hard to tell. But it's certainly true that names are more the underpinning of the internet than addresses. But I think it's something deeper than just the name system. I actually think what matters are referential frameworks. Because when we think about communications, we're actually trying to say, well, I'm trying to say to you, let me talk about this thing over here. Let me refer to that and pass that reference to you so you understand what I'm talking about. And the real challenge here, which I think is totally transcends AI or anything else, is this whole idea that as humans, we're pretty fuzzy with how we deal with concepts. We're very, very imprecise. And when we turn to the network, the computing, that environment of automated systems, they're very deterministic. And how do we join that highly deterministic computer-based symbol space into one that's usable by fuzzy and imprecise humans is, I think, the larger challenge of our times, which will actually absorb us for some decades to come. So that's all I've had. I've probably talked longer than I thought. So thank you for your time and attention. Again, I'm so sorry for not being there, but I've hurled enough rocks at v6 and the entire concept of addressing that there must be a question or two. So I'll happily take them. Thank you very much.
Thanks, Jeff. TCAP, would you believe me if I told you that Jeff was pre-recorded
Oh boy.
and that he is online on the chat for Q&A.
That's just fine. We'll try again later.
Yeah. And would somebody please type to Jeff, thank you very much for doing that? Since I can't type and talk to you folks at the same time. I know, I left my phone on the table. That was awesome, and I really don't believe Jeff. I think V6 is going to be the future. I've believed that since before my now legal adult child was born.